vast majority of irrationals have an irrationality measure of 2. So what do you mean by vast majority? How are you measuring the number of them? Is it
that's tricky.
Thing or a probabilistic thing? Or what?
That's tricky, actually. What I mean is that most of the time we've only found very few numbers, like most algebraic numbers, for example. Yeah, most of the ones that we've discovered have an irrationality measure of 2. Now, a few of the more exotic ones, like pi, I think pi actually had an irrationality measure of approximately 7.2, which is pretty exotic. But most of these numbers have a very ordinary irrationality measure.
So it hasn't been quantified.
No.
As far as how many. Okay, all right. Thank you.
Of all of the interesting irrational numbers, the vast majority of them have irrationality measure 2. But technically, the vast majority of numbers are irrational. So.
Great, thanks. So I have a question about the rate of convergence of the upper bound. Upper bounds are found. So you said that this is a new alternative way to bound things. So I was wondering, how would they compare this approach in terms of rate of convergence?
Oh no, this is not like a new way to do things. This is not a new way to bound things, right? Because the other approach is to first show the actual value of zeta of 2, which is pi squared over 6, which you can do with a lot of complicated trigonometry. And then you don't really need an upper bound. All you need to show is that pi is not only irrational, but also transcendental, which is a little more tricky. But that doesn't really rely on a rate of convergence. Doesn't rely on a limit or anything. It's straight to the point. Thanks. Yeah.
That was the number I was trying to remember last semester. I was trying to tell you about Apricot, but I forgot about it. I forgot what the name was, so I sounded like a raving lunatic. But so I'm very excited when I heard Zeta 3.
So, like you said, most of the interesting numbers have that irrationality index of 2.
Is a very exciting proof. I was very excited once I understood it for the first time, and I hope that learning this proof, even if maybe you've already seen it, or you've seen the other proof where you first prove that it's pi squared over 6, you die, and then you wait 50 years to prove that pi is irrational. If you've seen that proof too, I hope that this alternate proof that came 200 years later and is 10 times less efficient also works and is a lot more enlightening in the more exotic areas of number theory. But this is a blueprint that you can use for lots of other numbers, most notably Zeta of 3, which is the real thing that propelled Professor Roger Opry to fame. I mean, everybody already knew Zeta of 2 was irrational in 1979, because by then it was proven that pi is transcendental. But Zeta of 3 was an open box because Euler actually couldn't figure out a closed form value for it. He couldn't prove that it was irrational at all. So he just gave up, and 200 years after his death, we finally found someone who was ready to give it a go with this more convoluted technique. And now people are trying to use this to attack other odd values. Zeta of 5. Unfortunately, Opry died in 2007, so he wasn't able to get to this problem. Proof that Opry gave was not actually this long. He condensed it into about a page and a half, which means that a bunch of steps were skipped. I mean, the packet that I have on me right now is 15 pages, which made his very terse explanation very hard to comprehend. But with a little bit of help from Professor Zudlin, Professor Vadim Zudlin, he's one of the best mathematicians in this field right now. Many thanks to him for helping me understand this and also understand the proof of Zeta of 3. There were a bunch of open problems in this field, and this is just one of them. But it's one of the first things that told us that pursuing this field might be more viable, because back in the 1750s, Euler proved that Zeta of 2, Zeta of 4, Zeta of 6, etc. all the even zeta values were expressible as pi to the 2n divided by some integer, which meant that once we showed that pi was transcendental, people were able to say certifiably the even numbers were irrational when plugged into the zeta function. But then pretty much no progress occurred for a good 120 years until we showed that zeta of 3 was irrational. And now this field is open again, and people are trying to attack all of these other problems. But who knows how long it'll be until another discovery takes place. It's been 50 years since Opry made his discovery, and so far the best we have is that one of the following numbers, no, can't write it like that because it'll become confusing. One of the following numbers is irrational. This is just about the best we've accomplished in the past 50 years. But hopefully we'll be able to do something more in the next few years, and hopefully this problem will be cracked when I'm still alive to see it. Thank you. My name is Suborno Isaac Berry. I'm 12 years old, and currently I'm a bachelor's degree student over at New York University, where I'm officially going to be graduating in spring of 2026 with a math degree. So I'm very excited to be presenting here today. I'm just going to cut my own introduction short because this is going to be very, very long. Hi. So I've always been interested in number theory, and I think this lecture is kind of the culmination of all of that, because it took lots of effort to write down and understand in a way that I felt comfortable with and a way that I thought would be easy for others to digest. So it's going to be a little bit of a process to show that this number is irrational. So we start with, of course, the definition of irrationality, which is just something that's not rational. So a number alpha that can't be expressed as the ratio of two numbers like this, such that P and Q are co-prime. And of course, we represent the set of all numbers that can be expressed this way, like this. So the set of irrational numbers just looks like this. And of course, sometimes this definition, we can't write it as P over Q, is all we need for things like, for example, a proof of by contradiction. Now, I'm sure 90% of you have seen this proof by contradiction, but I think it's still worth reviewing. So, we can show that the square root of 2 is not rational, the most famous irrationality proof probably, by just assuming that it's rational, then multiplying by q on both sides, squaring, and using a little bit of number theory to realize this is an integer multiplied by 2, hence p squared must be even, since it's divisible by 2. But if p squared is even, that allows us to deduce that p is even. Now, if p is even, that allows us to deduce that p squared is divisible by 4, which allows us to deduce that then q squared over 2 is equal to p squared over 4. And this is an integer, which means that q squared must be divisible by 2. In other words, q squared is even, and hence q is even, contradicting the initial assumption that the square root of 2 could be expressed as the ratio of two co-prime numbers, because clearly both of them are divisible by 2. So that's the quintessential irrationality proof. Pretty sure everybody's seen that before. But now, sometimes that definition just doesn't suffice. For example, with very exotic numbers like zeta of 2. So, what other definition of irrationality or criteria can we use in order to establish that something is irrational? Well, all comes down to a very nice thing called irrationality measure. So here's the paradoxical thing. let's say I have the square root of 2, and I want to approximate it via fraction with denominator 1, let's say. So, when we're dividing by 1, we have a very rough grid of options, just the integers. And the square root of 2 falls somewhere in here as about 1.4142, I think. So, that means that the closest we can get is just saying it's approximately 1 over 1, since 2 over 1 is farther. You get even farther no matter which direction you choose. But now, let's say we raise our precision. Now, if I make the denominator 2, suddenly I have a lot more options to choose from, etc. And now you can see that the square root of 2 falls much closer to 1.5 or 3 over 2 than either 1 or 2. Then you can cut it into thirds, which I'm not going to visualize here. And you'll notice that, 3 thirds is 1, 4 thirds is 1.3, etc. 5 thirds is 1.6, etc. And so on and so forth, which establishes that 4 thirds is the best choice to go with. And you can actually assemble this pattern for the next few integers. So just writing down what I have noted so far, there's 6 for a denominator of 4, 7 for a denominator of 5, 8 for a denominator of 6, 10 for 7, so on and so forth. And now the main idea is that as you make these denominators bigger, there's more precision that you can use, and thus p over that denominator will be closer and closer to the square root of 2. And actually, you can make a graph of how the numerator changes versus the denominator. So, something like this, q, and, okay, it's a little bit too high for me to reach, so this is n, let's say, or q, and this is p, such that p over n is as close as possible to the square root of 2. And I've actually written a nice Python program to demonstrate that it falls off really fast. Now, I know you guys can't see from here, but essentially it falls off at a rate of about 0.421 over x squared, or n squared, let's say. And actually, this is not what we're graphing with. We're graphing the square root of 2 minus that, where p is as good as possible. Okay, so these rational approximations get better quadratically. So this is pretty nice. But now you can try doing the same thing with some rational number. Now, I picked some really crazy rational number. I just picked a random 4-digit number for the top, and then I picked a random 3-digit prime for the bottom. And I picked a prime because otherwise, if you had something like 35 over 24, you can actually get reasonably good approximations, like, for example, 9 over 4 very quickly, because this is a divisor, 24. But if you're able to do something like this, the error fall off is actually much slower. And you will see comparatively, it falls off at about a rate of 1 over x. Now, this fascinating thing tells us that rational numbers have an irrationality measure, which is a concept that we use to show how hard it is to approximate something, of 1. Because, of course, the exponent here is 1. And right here, we show that the square root of 2 has an irrationality measure of 2. In fact, the vast majority of irrational numbers have irrationality measure 2. Now, we don't really need to focus on specifically what the irrationality measure is. All we need to show is that that measure is greater than 1. So, if we're able to show that it falls off at a rate faster than any rational number would, then we've already completed the proof. So this is our main goal. Now, what is the zeta function in actuality? What does this do? Well, without any analytic extensions, the zeta function is very plain. It just tells you, it's kind of like a p-series actually, that you studied in Calculus 2. So this is the very basic definition of zeta. And for zeta of 2, you don't need any fancy analytic extensions that allow it to work for the imaginary numbers or complex numbers. Zeta of 2 is just this summation. And of course, we already know that this number has to exist because we proved that for s greater than 1, this series converges. That's what the p-series theorem tells you. But what do we do with this? How can we actually prove that it's irrational? Now, you can go the Euler route and prove that it's pi squared over 6. Then you can die and wait 50 years for someone to show that pi is actually irrational. Or you can go the faster route and not calculate its value and show it's irrational the other way, which was done by Roger Apéry, a very famous French mathematician who became famous for exactly this, all the way in 1979, about 200 years after Euler. So, this is actually a very neat result. So how does this come about? And actually, the sum doesn't stop. Not sure why I added a final plus. So, how do we actually go about proving that this is irrational? Well, our goal is to work with the irrationality measure concept to show that that best possible rational approximation will fall off faster than the denominator of the approximation itself. So this is commonly known as, I believe, the Liouville criterion. Okay, so can I move to the other whiteboard or? Okay, thanks. So, might be a little frustrating. Thanks. I'll keep this here. Let me actually see if there's a better marker than this. I'm just gonna grab this, that. Okay, so we're going to start by just defining a very nice series that converges to zeta of 2 itself. So we're going to start by expressing zeta of 2 as a nice integral, right? So zeta of 2 is this at its core. And so we can actually break it up into something like this. And now we can do something a little bit outlandish. Now this, of course, is equal to and I mean this is very intuitive, since for n is not equal to 0, which is what we're dealing with here, since this sum starts at 1, for n is not equal to 0, this is going to go to 0, this is going to go to 0, the numerators here are going to go to 1, this all works out, right? And that's pretty clearly looking like the evaluation of bounds of this function, right? So x to the n over n from 0 to 1, x to the n over n from 0 to 1. So that allows you to rewrite this as an integral. Minus 1. And we can multiply this by another integral right over here. Now I'm using this to distinguish them. Last time I gave this lecture, I did this, and it became very stressful and hard to keep up with. So, going to use x into y instead of x1 and x2. So, now we can do something even nicer, right? Because this is, of course, equal to, we can't do that. So this is, of course, equal to integral of this product. And this works because we're not integrating two functions of the same variable. This is x, this is y. So we're able to write it as this instead. Okay, and now we can use a nice property of sums and integrals. So, you guys know that the integral of a plus the integral of b plus the integral of c, etc. is going to be equal to the integral of a plus b plus c, etc. Linearity. In the same way, we can extend that principle. Oh, that doesn't look nice. We can extend that principle to infinite sums, just swapping out these two. And I'm actually going to put parentheses around this because it makes it easier to write. And now we can do something even cooler, right? Because what is this? This is xy to the 0 plus xy to the 1 plus xy to the 2 plus ... This is an infinite geometric series. And we all know that infinite geometric series, when of course xy is between -1 and 1, which is technically true by the bounds of these integrals, I'll get to that later, this just converges to 1 over 1 minus xy. R0 plus R1 plus R2 ... converges to 1 over 1 minus R. And we're using that same principle here to construct a nice unit square integral that perfectly represents zeta of 2. Okay, nice. This is wonderful. But can we do something? Oh, if I erase this, there's going to be so much smudging. Let's just... Alright, so now that's the actual zeta of 2. But our intention was to construct a sequence of rational approximations that converge onto zeta of 2. So, I mean, zeta of 2, naturally, is the infinite sum of rational numbers, right? N equals 1 to infinity, 1 over n squared. 1 over 1 squared, certifiably rational. 1 over 2 squared, I think we can say it's rational as well. 1 over 3 squared, pretty sure it's rational. And we can continue going. And of course, a finite sum of rational numbers is also going to be rational, which means that all the partial sums of this guy are going to give us rational numbers. So let's see if we can express that. Like, I guess I can use the notation AP, where P is the number of terms we're summing. So can we find a new expression for this, which is now akin to this? Go with that. This is going to look like 1 over k plus 1 squared plus 1 over k plus 2 squared plus ... doesn't end. So, of course, we can rewrite this as this. So, from there, we can use the geometric series trick again. This time, no, it's not backwards this time. So, nobody can see it from this angle. Pretty sure. We can write this as 1 over k plus n multiplied by 1 over k plus n. And now we can use the geometric series trick to rewrite this as the integral of 0 to 1 x to the k plus n minus 1, 0 to 1 y to the k plus n minus 1. And I think from there, you don't really need much justification for the next steps we're about to take until when we get here, what we're going to do is, well, first, switch these out like before. And then we make the realization that we're summing over n. The k has nothing to do with this. What we can do is just take the xy to the k out of the summation. And now this guy is starting to look a little bit familiar. It's just this within the bounds of our integral. And so, we suddenly created an equation for the difference between our partial sums and the actual number. My God. And I call this AK, all the way up there. Now, I don't suppose I can write very easily over there, so I think I'm going to pivot back here. Alright, so now we're going to do something a little bit weirder. We already know what 1 over 1 minus xy is going to do. We already know what xy to the k is going to do, but what if we change the powers on x and y? Does that give us anything special? What if we did something like this? What does this evaluate to? And it turns out something special involving zeta of 2 as well. So let's try assigning a meaning to this. Instead, since we're going, last time we went from an infinite sum to an integral. This time, we're starting with an integral, so naturally, we want to go backwards in order to assign meaning, and make this an infinite sum. So this is equal to, from 0, 0 to 1, 1, xa, yb, the sum of xy to the n minus 1 from n equals 1 to infinity, blah, blah, blah. I think we already know how this goes, so after having done it twice, I'm going to skip to this step. Wait. Oh, crud. Oh, okay, yeah, it's just variable substitution confusion. Use an M instead of an N in my writing for some reason. So I think it might be more useful to just get that and do this instead. So we get this right over here, and then this is equal to, we go back and write this as x to the a plus n divided by a plus n, and then y to the b plus n divided by b plus n. Okay. Oh my god. Oh yeah. From 0 to 1 and from 0 to 1. Okay. And now this is just n equals 1 to infinity of 1 over a plus n, 1 over b plus n. And suddenly, we've converted this back to this. And we can even do a sanity check and show that if a is equal to b is equal to 0, like we expect, this just reduces to zeta of 2, since it's just 1 over n times 1 over n. Okay, so I think I'm going to erase this. It's been up on the board for long enough. And now, we're going to do something pretty cool. So, the point of all this seems moot so far, but soon we're going to show that this guy actually will have a very crazy integral that evaluates to something like this. This is a secret. I'll tell you about it in a second. And then we're actually going to constrain that between this, which I'll also get to that in a second. Looks terrible. And this, and we'll soon be able to show that the rational approximations to zeta of 2 actually converge much faster than 1 over x. In fact, they converge kind of at this rate. Sorry. So, this is what we're setting up towards. Now, how do we get there? Well, what we're going to do is we're going to express things like these in terms of this secret variable that I'll tell you about later. So, this is just what? Now, without loss of generality, let's just assume that A is greater than B, because clearly this is symmetrical. It doesn't matter if A was named B or if B was named A. So, without loss of generality, assume A is greater than B, or equal to, who knows. Then we can write A as B plus N for some positive integer N. And of course, also note that if A is equal to B, this reduces to 1 over N plus A squared, which is another sanity check, because that's exactly what this integral was, right over here. just the error in partial sums. Okay, so A is equal to B plus N, right? So now we're going to write this instead as 1 over B plus N times 1 over B plus N. And you're probably thinking right now, what are you doing? You killed off one variable and replaced it with a newer, more confusing variable. So, what are we going to do with this extra N? Well, we're going to use partial fraction decomposition. So, this is, of course, equal to this. And now, we're going to say this is equal to, what variables can I come up with? N is already taken. J over B plus N plus K over B plus N. Now that implies that J times B plus N plus K times B plus N divided by is equal to 1 over that same thing. Or in other words, without the denominators, this is equal to 1. So, how can we determine J and K? Well, with the knowledge that these guys are all positive integers, we're able to boil all of this down to A.
Excuse me,
Sorry.
Judy, the multipliers should be switched, the B plus N and the B plus N plus capital N are on the other side.
You're correct. Oh my goodness. Thank you so much. I honestly don't know how I made that trivial of a mistake. How can we find out a value for J and K? Well, if we actually plug in the values, J is equal to, I'm forgetting how I wrote my own notes. This is not good. So, if we substitute in 1 over N times B plus N, and then minus 1 over N over here, what does this give us? Well, it gives us B plus N times N minus B plus N times N over N times B plus N squared times B plus N times B plus N plus N. Okay, and then this just gives you N squared plus N times B plus N minus N times B plus N divided by N squared times everything we were already expecting. Not sure why I totally forgot how to do partial fraction decomposition. So this expectedly gives us what we need. Okay, so now what do we do with this? Well, we rewrite the sum like this instead, as 1 over N times B plus N minus 1 over N times B plus N plus N. And now what we want to do is, since N is not being summed over, big N is not being summed over, we can just factor it out over here. It's just a constant after all. So now, find it necessary to keep these lines, but those ones are kind of important. So now, what can we do with this? Well, if we substitute in another variable, this time for B plus N, let's say, let's call it C, who knows. So 1 over N times this. But suddenly, N has disappeared from the summation to begin with. We're going to need to substitute in something else. So since we made C equal to B plus N, I see no reason why we shouldn't just be able to write C is equal to B plus 1. Okay, that works. And now that gives us what? Well, ignoring this term, since it's a constant, we'll add it back into the soup later. What does this give us? Well, it's going to be 1 over b plus 1 minus 1 over b plus 1 plus n plus 1 over b plus 2 and minus 1 over b plus 2 plus n. And after a little bit of foreshadowing, you'll figure out that this is going to be 1 plus b plus 1 plus n minus 1 over b plus 1 plus 2n plus 1 over b plus 2 plus n, etc. And then you'll realize that these guys are going to get their own 1 over b plus 1 plus 2n minus 1 over b plus 1 plus 3n. And in actuality, all of these alternating terms kind of telescope. And wait, no, you can't cancel out things that indiscriminately. That's a mistake. Okay. Now that we fixed that up, we can cancel out these. And you'll quickly see that all that's going to be left is 1 over b plus 1 plus 1 over b plus 2 plus all the way to everything before this guy, which is the first thing to get canceled out, which is going to be 1 over b plus n. This is all we're left with. And wait a second, b plus big N is a. So really, this is just 1 over n. No, but we're already using n. I'm going to call it I, from I equals b plus 1 to a. So let's get rid of everything here, since we've resubstituted in all of this. And now we suddenly have that this right here is equal to 1 over n, but what is n equal to? Well, we defined a is equal to b plus big N earlier, which implies big N is equal to a minus b. So you have that this just became 1 over big N times the sum of 1 over I. Now here's what we can do. This guy can be restricted with its denominator. And we're going to introduce something called, well, it's not a very new concept, the least common denominator of the first n consecutive numbers. And we're going to abbreviate this as dn. Now, to show how this is going to be useful, let's first start by looking at the simpler case right over here. Well, no, right over here. So, what does AK look like? Well, it's what happens when we add up a finite number of these terms. It's going to be 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared, dot, dot, dot. And all the way to, let's say, 1 over k squared. And expectedly, this is going to give some number on the top, I don't know what it is, divided by the least common denominator of 1 squared, 2 squared, dot, 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 k squared. But
So, Gordon, excuse me, those aren't fractions. So what do you mean by the least common denominator?
oh my, least common multiple.
Okay, got it.
Not sure how I got those confused. So this is actually equal to, unbelievably, this. Yes, I'll rephrase that. squared. And this is a very unlikely relationship. This is going to get smudged. Let's do it anyway. But it actually works because of how the least common denominator works. Oh, so the least common multiple. Now, what does this do effectively? Well, let's see by looking at a simple example with 7 numbers right here. So, this is the least common denominator of 1, least common multiple of 1, 4, 9, 16, 25, 36, and 49. Now, what we're doing is looking for some number that's divisible by all of these. So, some number that's divisible by 1, divisible by 4, divisible by 9, divisible by 16, etc. Now, note that that does not mean that they're divisible by the entire product. 99% of the time, the least common multiple is not divisible by the product of all the numbers. So, how do we find that least common multiple? Well, first, the least common multiple, like all numbers, has a prime factorization. And when we're checking for divisibility, one of the first things we do is check the prime factorization. Like if we want to see if A divides into B, we check B is 2 to the 5, 3 to the 2, 5 to the 7, 7 to the 16. I don't know. Then we want to check, is the power of 2 in the prime factorization less than or equal to 5? If so, is the power of 3 less than or equal to 2? If so, is the power of 5 less than or equal to 7? If so, is the power of 7 less than or equal to 16? And if all of those are satisfied, we've gone through with the decision. B is indeed divisible by A. And in the same way, we're going to be doing that check on each of these. So we're constructing some number that's divisible by 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, and 7 squared. Now, what's nice about these is that checking the non-prime numbers, they can be decomposed into 2 squared, 2 squared, and 2 squared, 3 squared in this very simple example where about half of our numbers are prime. Well, actually only 2 of them are non-prime. One is not neither composite nor prime. I digress. So, now, how do we work with the least common multiple of these? Well, first, we search up which of these guys has the highest power of 2 in their prime factorization. And well, that's 4 squared, which is 2 to the 2 times 2, which is 2 to the 4, of course. I guess I'll actually put something like this. So, how do we work with this? Well, that least common multiple now has to have that power to the 4 inside it as part of its prime factorization. But wait, 16 isn't divisible by 7 squared, or 6 squared, or 5 squared, or most of these numbers except 2 squared and 1 squared. So we got to add some more factors. Next, we search up which of these has the highest power of 3 in its factorization. And that's, well, 3 squared and 6 squared. They're tied. And then which one has the highest power of 5? 5 squared. And which one has the highest power of 7? 7 squared. But what you'll notice is that each of these numbers is just the squared prime factorization. And actually, this is going to sound like nonsense. So, if we take the square root of all of these, we're left with this. But that's just the prime factorizations of these numbers. So, in fact, that x is actually just equal to this squared. But wait, this the very definition of the least common multiple of 1 through 7. So because of the way the least common multiple works, this is actually equal to the least common multiple of this squared. But we can do even more, right? What we can actually do is show something nice about the least common multiple. And from now on, we're going to denote it as dn for this because I'm getting tired of writing this. So, what do we do with this? Well, the prime number theorem tells us that, I'm not going to cover the proof of the prime number theorem, it's not in my notes, and it's also going to go over the time limit. So, this is the prime counting function. Tells us approximately, well no, not approximately, exactly how many primes are less than this n right here. So, for instance, pi of 10 is just going to be, well, there are 4 prime numbers under 10. Pi of 100 is going to be 25. And in fact, it's been proven that pi of n is approximately n over ln of n. Now, in actuality, it's a little bit closer to n over the floor. No, the floor of the entire function. So, we're not going to cover that because that makes things a little more complex than they need to be. So, this is what we have. And now we know that this does funny stuff with prime numbers. So, in specific, dn as well, this is just for all primes less than that n itself, we're kind of looking for what? Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, if, for example, 3 cubed is 27, that's greater than 10. There's no possible way a single one of these numbers are divisible by 27. We can say that. 2 squared is 4. There has to be a number somewhere in here that's divisible by that. And of course, there is. Because this contains every number, including primes, and the powers of primes between 1 and n. That's the power of being consecutive. So, there must exist some, 3 squared is 9. That's less than 10. Thus, there must exist some number here, of course, that's divisible by 3 squared. And the cycle continues. So, we're going for p to the k, where k is, the maximum, k is the maximum integer, such that p to the k is still less than or equal to n. And now that implies that k is just equal to log base p of n. Is equal to, by the log conversion theorem, well, it's not really a theorem, just a property of logarithms, log base e of n divided by log base e of p. And now that's pretty useful because what we can say is that k is less than or equal to ln of n over ln of p, which means it's also guaranteed that k is less than or equal to the floor of that. Which means that this, by definition, since p is always greater than 1, less than or equal to this. Okay, so now we realize, ooh, this is getting really smudged, almost a gray board. So now we realize that this is actually equal to the product of what? P is e to the ln p. So raising it to the ln of n over the ln of p is equivalent to just having e to the ln of n, which is n. And hey, wait a second. This is just the product of all primes that are less than n. So that means this is equal to n to the pi over n. Since we're counting up how many times primes appear before n, and then multiplying n that many times. But wait, this is approximately equal to n to the n over ln of n. And this is just e to the ln of n to the n over ln of n. Which means that dn should be less than or equal to e to the n. And just to make sure that this is a sturdy upper bound, because sometimes this happens to be greater than this, sometimes this happens to be a little less than this is strictly less than 3 to the n, which means that we can always say dn is less than 3 to the n. And actually, I ran another handy computer program which compares e to the n versus dn. And actually, if you want to see it, I have it right here. So see, this dot plot is dn, and this dotted line right over here is e to the n. So it's a logarithmic scale, which is why it appears as a straight line. And you can see sometimes it climbs a little bit over it, which is why we use 3 to the n. So now we have this useful fact, and we are also certain that ak can be expressed as some integer z divided by that least common multiple squared. Which means that, probably we can be 100% certain that this zk to the dk over dk squared has to be less than, or wait, greater than zk over 9 to the n. Okay, so now this all seems like we're starting to run away from the point. But the point is about to smack us in the face. How much time do I have left?
1 minute, 30 seconds. We can. How much more time do you need?
I'm going to give it 15 more minutes. Okay.
We are enjoying.
Okay. So you know what? I don't believe that I have enough capability to do this in 1 minute. I think the only person who can do that is my differential geometry professor. Fills up all 3 blackboards in 6 minutes. So I'm just going to say without justification, because we're not on the best time limit. This is going to be equal to, and I pray that you'll trust me in this, this is going to be equal to that integral from 0 to 1, this guy right over here, minus, plus this integral right here, x a y b. Technically means all of that was pointless since we didn't actually get to use it in the full proof. So now this is equal to what? Well, we know from all of the labor that we've done that's taken up 90% of the lecture that this is equal to zeta of 2 minus z sub k over d sub k squared plus, what was this right over here? Well, we demonstrated that it has to be some number. I'm going to come up with, have we almost used all letters of the alphabet? Oh, we haven't used Q yet, I think. What? Okay. No, I used alpha in the beginning as well. So we're going to switch to beta. All right. At least we don't have to get to Hebrew yet. So we have this right here, which can be simplified to dk squared zeta of 2 minus zk plus beta k over dk squared. And now, since this is an integer certifiably, this is an integer certifiably, we're going to say that this is equal to gamma k zeta of 2 minus delta looks like, no, that's sigma. I can't use the capital delta. Okay, we're moving, oh yeah, lowercase delta looks like this, plus, sorry, we don't need that, divided by, we're going to say dk squared. I think we can keep that right now. Okay, this is fine. We're doing fine. Okay, so now, all of the pages of justification that I have to skip. Now, I said I would prove that this is actually bounded by phi minus 1 to the 5, but that proof takes a full page and a half. What do we think?
I'll take your word for it.
Okay, we're taking words for it again. Right? So, the crazy integral that we have here is actually less than, wait a second. Let me see. Okay. Surprisingly, this works specifically for, sure, right now. Wonder what percent of this lecture has been taken up on flipping through my lecture notes. Yeah, okay. So, this can be taken as equal to, and you know what, yeah, just take my word for it. This is equal to a very horrible integral and demonstrably the integral, well, no, xy times 1 minus x times 1 minus y over 1 minus xy over the unit square peaks at phi minus 1 to the 5. Now, the proof that I'm basing this off of said this was a trivial exercise, so I'm hoping that you can take it the same way. It took me 2 hours to figure it out, but that was a trivial exercise to him, so. All right, so that tells us that this has to be less than, well, the absolute value of this, since we have this nasty term in front, the absolute value of this guy that goes straight through the delta is less than or equal to minus 1 to the k times the integral from 0 to 1, we put an absolute value so we can vanquish this. The golden ratio minus 1 to the 5th power. So that's another Greek letter out, I guess. Can't use that. To the n, because remember we have that on the outside. And this is a constant, so we're going to take it out. And this is k. Times 1 over 1 minus xy dx dy, which is exactly why we used that zeta of 2 integral representation in the beginning. This reduces to zeta of 2, as we saw way at the beginning of the lecture. And so now, since this is an absolute value, this is forced to be greater than 0. Well, yeah, since this is a rational approximation, we can't assume anything. This could be equal to 0 for all we know. So, smudging all this ink one last time, what do we get out of this? Well, phi minus 1 to the 5th power evaluates approximately, and so that's less than 0.1, which implies that this right over here, the absolute value of .1 k zeta of 2. And this is the moment where we realize I shouldn't have used gamma, because I could have just perfectly fine left it as dk squared, but whatever. So now we have zeta of 2 minus this guy, delta of k, divided by d sub k squared is less than or equal to 0.1 to the k zeta of 2. And now we use that crucial fact that we learned a while ago, that dk is less than 3 to the k, and hence dk squared is less than 9 to the k. And so now, what do we have here? Well, we have 9 to the k zeta of 2 minus delta of k is less than or equal to 0.9 to the k zeta of 2. Now, I would say pretty certifiably that this is an integer. And, I mean, we've defined this as an integer from the beginning. So, what does that mean for us? Well, 0.9k shrinks, rather, at a much faster rate than c over k, or I guess O, big O of 1 over k. But I don't have a full grasp on the definition of the big O function, so I'm going to play it safe and write it as c over k. So, this has to be true since this is an exponential function, which makes it much faster than just this inverse function right here. Which means that this is always less than, for sufficiently large k, of course. Which means that at some point, that criterion, no, we already used A, we haven't used epsilon yet. This is less than c over k. But wait a second, that definition of irrationality that we wanted to see a while ago. This looks strikingly similar to this. And of course, there's one thing missing, and that's the fact that I haven't divided by e sub k yet. For sufficiently large k. Because for small k, you can just make c like super, super huge. And then you have, for example, 1,000 over 5 is, no, but that's already, no, you can make c super, super small, like 0.01 over 5 is still a lot smaller than 0.9 to the 5. Don't fact check me on that. Let's say 2 instead. This is pretty correct, which goes to show you that this only works for sufficiently large k. But once we've hit the point where it works once, there's no gaps, there's no interruptions. At some point, for sufficiently large k, this relation is satisfied, and that's enough for us. We've already shown that zeta of 2 doesn't follow the same approximation rate as a rational number would. It gets approximated faster than a rational number by rational approximations, and hence, by the Lufel criterion that we demonstrated at the very beginning, it should be irrational. So, this is actually, I've went over the 15-minute extra, haven't I? Okay, that's fine. So this is actually used in lots of proofs of irrationality. Also, Lufel was the first person to show that transcendental numbers exist. So he's also a really great mathematician, even though he isn't mentioned as much as a lot of other famous mathematicians. But I mean, he's everywhere once you start getting and looking into number theory. So this is a very exciting proof. I was very excited once I understood it for the first time, and I hope that learning this proof, even if maybe you've already seen it, or you've seen the other proof where you first prove that it's pi squared over 6, you die, and then you wait 50 years to prove that pi is irrational. If you've seen that proof too, I hope that this alternate proof that came 200 years later and is 10 times less efficient also works and is a lot more enlightening in the more exotic areas of number theory. But this is a blueprint that you can use for lots of other numbers, most notably zeta of 3, which is the real thing that propelled Professor Roger Opry to fame. I mean, everybody already knew zeta of 2 was irrational in 1979, because by then it was proven that pi is transcendental. But zeta of 3 was an open box because Euler actually couldn't figure out a closed form value for it. He couldn't prove that it was irrational at all. So he just gave up, and 200 years after his death, we finally found someone who was ready to give it a go with this more convoluted technique. And now people are trying to use this to attack other odd values. Zeta of 5. Unfortunately, Opry died in 2007, so he wasn't able to get to this problem. They're trying to attack multi-valued zeta functions, which I'm not going to go over. You can look at it. There are a bunch of open problems in this field, and this is just one of them. But it's one of the first things that told us that pursuing this field might be more viable, because back in the 1750s, Euler proved that zeta of 2, zeta of 4, zeta of 6, etc., all the even zeta values were expressible as pi to the 2n divided by some integer, which meant that once we showed that pi was transcendental, people were able to say certifiably the even numbers were irrational when plugged into the zeta function. But then pretty much no progress occurred for a good 120 years until we showed that zeta of 3 was irrational. And now this field is open again, and people are trying to attack all of these other problems. But who knows how long it'll be until another discovery takes place. It's been 50 years since Opry made his discovery, and so far the best we have is that one of the following numbers, no, can't write it like that because it'll become confusing. One of the following numbers is irrational. This is just about the best we've accomplished in the past 50 years. But hopefully we'll be able to do something more in the next few years, and hopefully this problem will be cracked when I'm still alive to see it. Thank you. We're on negative time.
Yeah, I was gonna say.
We always have time for questions. I have a question. Back at the beginning, you said that the, let's see, what was you said the vast majority of irrationals have an irrationality measure of 2. So what do you mean by vast majority? How are you measuring
Yeah,
the number of them? Is it a
that's
Bayesian
tricky.
theoretic thing or a probabilistic thing or what?
That's tricky, actually. What I mean is that most of the time we've only found a very few numbers, like most algebraic numbers, for example.
The ones we discovered.
Yeah, most of the ones that we've discovered have an irrationality measure of 2. Now, a few of the more exotic ones, like pi, I think pi actually had an irrationality measure of approximately 7.2, which is pretty exotic. But most of these numbers have a very ordinary irrationality measure.
So it hasn't been quantified
No.
as far as how many. Okay, all right, thank you.
Of all of the interesting irrational numbers, the vast majority of them have irrationality measure 2. But technically, the vast majority of numbers are irrational. So,
Great, though, thanks. So I have a question about the rate of convergence of the upper bound. Upper bounds are found. So you said that this is a new alternative way to bound things. I was wondering how would they compare this approach in terms of rate of convergence?
oh no, this is not like a new way to do things. This is not a new way to bound things, right? Because the other approach is to first show the actual value of zeta of 2, which is pi squared over 6, which you can do with a lot of complicated trigonometry. And then you don't really need an upper bound. All you need to show is that pi is not only irrational, but also transcendental, which is a little more tricky. But that doesn't really rely on a rate of convergence, doesn't rely on a limit or anything. It's straight to the point. Thanks. Yeah.
That was the number I was trying to remember last semester. I was trying to tell you about apricot, but I forgot about it. I forgot what the name was, so I sounded like a raving lunatic. But so I'm very excited when I heard Zeta 3.
So, like you said, most of the interesting numbers have that irrationality index of 2, right?
Mm-hmm.
Or more. So can you give an example of something that does 1.5 or something?
Actually, I haven't heard of one with an irrationality measure of between 1 and 2 yet.
But it's possible.
I would think so. Oh, it's left to the reader.
That would make a lot of people mad.
Yeah. Whoever created well, it's not a creation per se. But no, I haven't heard of a number with irrationality measure between 1 and 2 yet. But maybe I'm just in the dark about this, and there's probably one that people have already discovered.
Any other questions? Let's thank the speaker again.
Thank you. Proof that Opry gave was not actually this long. He condensed it into about a page and a half, which means that a bunch of steps were skipped. I mean, the packet that I have on me right now is 15 pages, which made his very terse explanation very hard to comprehend. But with a little bit of help from Professor Zudlin, Professor Wasim Zudlin, he's one of the best mathematicians in this field right now. Many thanks to him for helping me understand this and also understand the proof of Zeta of 3. And I anticipated, thankfully, that we wouldn't be able to get to that, but I didn't anticipate that even this would take too long.
So that was in the 70s that this was proven?
79.
79, okay.
Mm-hmm.
Very much.
Yeah, it only took 200 years.
Yeah, it only took 200 years.
Yeah, like.
Oh, yeah. Oh, yeah.
They're
yeah.
donuts and coffee. Order.
I love,
Oh wait, there's soda? Oh, my mouth is super dry right now. Take that.
when I saw rationality.
Yeah, sure. And also thanks for taking the time to attend, Dr. Clark.
Yeah, I skipped one of my class for attending your meeting.
Oh.
Yeah.
Thank you.
Yeah. Are you going to? I got.
Yeah, well. Okay.
So I see 7 of you as a group doing that.
Yeah.
Smile.
Yeah, he's a great person. Right now,
Yeah, it was really, he found out that I have a side interest in physics. I'm a mathematician, not a physicist, but I'm interested in physics. And so he wanted to talk about physics. And after class, he would always ask me all these questions.
Look at the camera. Smile.
yeah, he used to love astrophysics actually. I think he still.
What's your name?
Thompson, Rob Thompson.
I mean, if you have the time, obviously.
So would you have time to give a talk to middle school students in our program on a Sunday?
Oh yeah.
You would? Okay, so
Could even be this Sunday. No, I could probably do groups. Those were pretty fascinating. And
do something with number theory.
oh, that would also. Be nice.
With numbers that it's like younger kids could understand.
Why don't
right?
you and him make a lesson plan together? That would, because you know their background, so they're not going to feel completely lost.
Yeah.
Yeah. So make a lesson plan together.
Yes. Well, if he gives me a topic, I'll tell him if it's suitable.
How tight is the bound between dn and 3 to the power n? You show that you show a figure.
Analysis 2 and complex analysis are not the same though.
Analysis
Yeah,
two is
I thought they were the same initially, but I've discovered they haven't.
They're very different, yeah.
They haven't mentioned complex numbers a single time yet. So
Although they make a lot of real analysis problems. Complex numbers, yeah.
I'd hope complex analysis is a little easier than analysis 2, right?
Analysis two is I mean analysis in real analysis in general is so intricate. It's very, very precise.
Thank you.
And, oh yeah, you're gonna decide, yeah. I'm sure
Great. Yeah. Did you send me the deadline?
yeah.
Okay.
Hi, nice to meet you.
Nice to meet you. How are you?
Yeah, I'm good.
You're from Bangladesh, right? I
My
mean, your parents are from Bangladesh.
I'm from here actually.
Yeah, I know.
All right, so we're just texting. I'm sorry.
Can you take a picture of the picture, please?
Yeah.
Do you mind?
Sure.
No? Do you mind? You want a picture? What?
Did I make it in there?
Can you take one more? Just one more. Okay, so thank you so much.
All right, so we're gonna get started.